Morning, everyone. Welcome back. Thank you for joining me again on part two of this episode. Um, Continuing on today with the topic of last week, the rat sequence, the reverse and then sort sequence by John Conway. So the idea being is that John Conway decided a plausible terminus or a natural terminus would be if we incur an integer within the series values where all the digits within that integer were the same. It seemed like a very logical, trivial stopping point for him, so it worked well for him then, and it worked well for us now. However, there are many such termini that one can use. Um, all we need to do is, I suppose, enact it and see how the behavior changes or how long these series values go for. I think it was after I created video last week, I had a bit of a brainwave, something which is in a bit of a short supply at the moment. So I'm making the most of this newly found inspiration. So you'll see this is the script that we wrote last week, and all I want to do is I want to build on it. It's this very bottom function here, the static bool, which it's the only thing that really needs to be changed. It's got two references, so I need to change those references above. So I think that's all. So let's do that. I have a few ideas of how this can go, so let's simply try those out. Um, close this down, and I'm going to copy this into a new instance of C sharp. Okay. Good. So new instance of C sharp, and all I want to do is change that. So let's try one thing. Let's start with prime numbers. So let's see, whenever we incur a prime number, the series stops. So you'll recall from the very first episode that we made, that was a simple prime number generator. So all we need to do is change that. So let's simply do that. How does one? Okay, so I'll keep the static bool, and all I want to do, if I remember it correctly, which I don't need to because I'm gonna simply try and freehand it, is be. I need the big integer now. So instead of that, I'm gonna try. Is it S or N? I need a big integer. Yeah. So, oops. Yeah, big integer. I'm going to use N instead of S because that'll make things a bit easier. Because I'm not using digit values in a string. So S is the digits within C, but we're not working with C. So I need if equals less than or equal to, no, less than or equal to 1. So return false. If, what is it? Remember, equals 2. So return false. Okay, return false. No, true. That's true. Okay, and what is it? If if the remainder, when you divide whatever n is by 2 is equal to 0, then that is a even number, and so at which point we return false. Okay, so remember, unlike episode 1, we weren't looking to find the divisor, so we didn't need to set a limit here. So you'll notice I had some limit function here, which I don't really need anymore. For I equals 3, so then I need to equate I. I is equal to 3, so we had the limit here, whatever that was, but we're not using the limit anymore. So I cross I, so the square, so that is less than or equal to n, no, n, concentrate, for whenever I is at spaced values of 2. Okay, so I need, good, so if n, the remainder of n divided by this I is equal to 0, so even basically, then return false. Otherwise, we return true. Okay. Good. Good. So we have 0 references here, and this is indicated down here. We have 2 errors, so we need to remove the above references. And we're going to have to do something else because we've used big integer, and I realized we didn't need big integer. I don't know why I used big integer. Sum, okay, and I need to do the same up here. So we don't need the toString because the prime is not necessarily, we're not storing that as a string of text. So I think that's it. So I think we can run this 1000. So what happens here? Good, okay. 1000, still divergent, no prime numbers it seems, possibly divergent, anything we've got finished. Okay, at 997, I guess that's a prime number. 988686889. I'm going to have to take its word for it. I guess that's a prime number. So here we've got 994, Oh, simple. 1493, that's a prime number. And I'm simply going to have to take its word for it. That's what I did back in episode 1. That stance was good enough for me then, it's good enough for us now. 1, 2, prime number, yep. Divergent, everything is divergent. I guess we don't run into prime numbers. 11, and yeah, I'm well aware that 11 is a prime number. What if we, I don't know, what if we increase the number of steps to 100, let's say? I'm not sure if this will run cleanly or neatly, and I don't even think we need to go to 1,000. It stops after 12. You see, everything. I wonder what the limit is. Like 8 here. Oh, I don't think we had that. 7227. 7. It did not terminate after 40 steps. Finish. Neither did 4. Neither did 2, I don't think. Let's take 4, actually. 4. So remember this. Not 4 even. It finished. I don't think that was the case here. At 40. So, I mean, it's a case of increasing the number of steps, I suppose. 1, 2, 3, 4. Possibly divergent. Yeah, okay. Good things come to those who wait, or at least increase the max action count. Okay, so let's try something else. So there we go. That's interesting. Okay. Next, let's try something else. So I'm going to control Z's a bit now until I restore the 2 strings. Okay, good. So let's try something else. So I mentioned this word palindrome a lot. So a palindrome is any number, integer, sequence, word, sentence, etc. that is the same. It's you read it the same forward as you do backwards. So 121 or 12,321, or the phrase never odd or even. Never odd or even. Yeah, I think so. Palindromes. What is that? Never odd or even. So I think that's palindromic. So again, ignore spaces, ignore punctuation, ignore capitalization. I'm going to get back and concentrate here. So palindrome. So we want a palindrome. So whenever we hit a palindromic number, concentrate. So what exactly is a palindrome, or how do we recognize a palindrome? Let's create a new function. A palindrome, palos in Greece, meaning again or continue. And dromos, meaning to a course or to run, etc. So a place where we run again. People might be familiar with a hippodrome. Maybe you've walked past Leicester Square and you've seen the hippodrome building palace on Cranbourne Street. Cranbourne Street, incidentally, was the original name of Leicester Square Station, but I suppose Leicester Square was more iconic and people spent more time on the actual square itself than on this tiny road called Cranbourne Street. So that's all I have to do. No issues found. So I'm going to run that. I'm not sure what we get. But remember, we had a few palindromes after 40. So let's see. So that's, yeah, look at that. Everything seems to end. And a hippodrome is originally in Greece, where people would run around on horses. Hippos meaning horse in Greek. Time I came close to that when I was in Peru many years ago. I was on the Urubamba River, staying in a nice, peaceful lodge. Oh my goodness, it was such a beautiful place, the Urubamba in Peru. And I was chased by an alpaca. Um, well, I certainly wasn't riding it. That's the closest I'll ever come to riding around on horses. It's not like Hannibal and his elephant. Oh goodness, well, I don't know. What did I do to deserve to be chased around by an alpaca? Anyway, I'm gonna get back on track here. So you see, we all hit a palindrome at some point. There you go. So 2, 4, 3, 4, 6, 4, 5, 8, 5, 4, 4, 4, etc. I mean, look at this. Everything hits a palindrome at some point. I don't think there's anything that simply diverges. I think everything ultimately finds. I think that's it. There's no divergence. I mean, I think that's a classic case. You're adding, um, you know, how do you even describe this? I mean, it looks logical even when you reverse the numbers and then you add them up to the original. I don't know. Maybe someone can articulate that better than I can. If someone in the comments can maybe explain it, please do. No divergence. Look at that. What if I raise the stakes a bit more? Let's try. I don't know, like what happens? 1,000 to 2,000. Let's see. Do we get the same? Divergence, divergent. I mean, you recall one of the good things about working in programmers was that we can control F. We can't control F here, but everything seems to converge. So that's good. Um, Next, what can we try next? I'm going to restore the palindrome. Okay, so what do we want to try next? What about a square number? What if we say whenever we hit a square number, we stop? So is perfect square squarism? By definition, a square is a square. It's not. It's something more of. Oh, forget it. It doesn't matter. Okay, I'm here now. So var n equals varena varena. Okay, so pass s. I'm going to try and pull through that s. So whenever we hit, 1, 4, 16. No, what comes after that? Yeah, 1. Return false. I'm just going to write this out real quick. Okay, so big inter. Sorry, I need to turn that integer. Yeah, math dot square root double. I was trying this out. I think I figured this out yesterday. Just want to if I remember it. Root times that root, which we've already defined, is equal to function n pass it legendary. So what is that? If it's a perfect square, otherwise return. Yeah, okay. So root plus 1 times root sorry, plus 1. Okay, that's equal to n. Okay, so it's basically a square number. Okay. So I need to remove the references. So I can't imagine anything would come of this. So what are these like 1, 4, 9, 16, was it 35 plus 1, 49, etc. I can't imagine these numbers would appear. They're very few and far between. Is perfect square. Come on, concentrate. All digits the same. So again, get rid of that. Let's simply run this. I mean, yeah, possibly divergent. I can't. There's no convergence. Oh wait, no. Here we go. 1461. It's a palindrome and it's a square. What is that? That's 1461. I'm going to get out my trusty BA Texas Instruments 2 BA2 plus. What is that? That's 121 square, which is also a square. That's 11 squared. That's 11 quadruple. Sorry, quadruple. Yeah. So what is that? 1089. What is that? Squared. 1089 rooted 33. Maybe there's a pattern in here. I have no idea. Maybe someone can read into this. Let me know if there is some sort of pattern. Divergent, divergent, divergent. A lot of divergence here. I mean, yeah, there aren't really many prime numbers. Well, there are many prime. There's an infinite number of prime numbers. So 1089. That's again 33 squared. I think that's it. Yeah, it's pretty good. I know we can't even. You see, yeah, what is it? The PowerShell or the command prompt. It's not even letting me go up. It's sort of erasing the previous progress. So we can't view it, but I'm guessing there's simply a lot of divergence because we're getting at least 40 steps. All the max action counts is taking up space on this PowerShell, which is why I can't see the whole log. But I'll take its word for it. I don't know what happens in the first 100. Do we get any such convergence here? 4 prime. No, square. Sorry, did I say prime? Square. 121. Good, good, good. Okay. Okay. I'm not going to spend too long on this, but I'm going to try just a few more things. Square. What else do I want to try? Cube. Oh yeah, let's try cubics. So I'm not going to go all the way. I simply want to see. We had a few squares, but I seriously doubt they were going to be cubes. Okay, so cube is cube string s, and this will require a bit more in terms of lines. So I'm gonna okay, just get that out of the way. Okay, so if n less than 0, so if n less than 0, return the false. Okay. double root approximation. So now we're going to introduce this root, which it will be power. Okay. Now, I couldn't find a way to get around this, really. I'm not entirely sure why we had to use this notation. But basically, this is cube rooting it. So 1.0, 3.0. So remember, I don't think it works if you simply type in an integer without a decimal. So I simply want to avoid those problems. So integer root. If the root here equals the new big integer root approx, yeah, then what does that return the root? That cube root. Return it only if it's cube root. Oops, there is a concentrate root root. What's to that? N. Yep. I'm not saying new. Why have I put new here? Something is not correct. Name of, that's simply supposed to be N. Solve any problems? Nope. Gotten this. That's not solving any problems because I still need to is cube even. That would be very helpful to get that correct. I still have some problems. Okay. Is cube same? Yep. And is cube the same? And here I seriously doubt we are going to get any cubes if N doesn't exist. Yeah. N. N. Sorry, I was supposed to change that to N. Okay. Now, what's your problem? Operator cannot be. Y. If N. No, I changed it to N. String integer. Big. Oh. Cannot convert. Why not? Because big integers. Oh, because it's also a big integer. Oh yeah, I need to just get rid of you and get rid of you. Okay, and what is your problem here? I needed to put a semicolon there. Again, things that you couldn't do in programmers. Okay, so let's do that. Okay, so that is simply nonsense. I seriously doubt there's any cubics in there, and we are tapping out at 132. So again, I seriously doubt it. These are all divergents. Is cube. So let's sort of try something else. I don't want to see all of these is divergence. Let's simply cut out all these windows. I think you get the point anyway. What the sequence is. Start, reverse the number, sum 975 and 579. Sort the digits, sort those digits, and you simply do the process again. So let's simply keep that in mind. And what I want to do is I simply want to remove the intermediary lines. I've had enough of them. I don't want to see them. So what do I need to do? I need to add, let's say, some sort of if function, but only once applied after all the steps are done. That's not the best way to say it. But the step log function, if anyone's familiar with the step log function, let me know. Also, anyone from Peru, or if anyone's been to the Urubamba in Peru, please let me know. If you've been chased by an alpaca before, please let me know. Okay. Okay, so I need that. That's a string build. This step log allows me to simply state an if, but only after I've carried out all the steps. So I don't want it to run the if while we're actually carrying on with those steps. Otherwise, well, we don't need that function. We can do that, but that's not what it's for. So I simply change output where I see it to step log. Okay, and I simply do that for all instances of output. Not really, actually. That's not entirely true. Step output. Yeah, current output. No, wait. What did I do here? Yeah, no, okay. So all of these out here, if the step count, append. Yeah, okay. I'm gonna get back on track here. Step log. Okay, step log. Step log. Okay. Step log. Step log. Okay, and I need to change this line here because this is still running with output. So I don't entirely need to dismiss it. In fact, I might want to even keep it. Um, okay. If the end message contains this phrase divergent, not if divergent, um, divergent. No, go away. Good. Well, not good. So that's where I want to add this, or I'll keep that. Yeah. Else. Oops. Else. Um, output. Append step log dot to string. Okay. So if it does converge, then we can output all of those lines. Okay. Output dot append end message. So let me sort of explain that. Return output string. I don't know if the positioning matters. I'm going to not indent it anyway. So if it contains the word divergent, then you simply omit all of those lines. That's all it is. And you simply go to the end message, whether it be possibly divergent or whatever that final output is. Otherwise, if it does not, simply do output all of those. So all of those lines, all of those two strings. So I think this is fine. So let's run this. Remember, we're running this for cubics. Good. There we go. So I think that's it really. There's absolutely no convergence. There are no cubics in this sequence at all. Oh, wait, I saw that. 343. There you go. Reverse 343. And what is that? 343 to the power of. I can do fractions on the Texas Plus, but that's 7 cubed. Okay, that's 7 cubed. Okay. 343. Again, that's 7 cubed. Is there a theme here with 343? 343. 343. Interesting. So we only get 343. So that's 7 cubed. There we go. There's our number. 7 cubed. 7. Any reason why this is 7 cubed is the only one apart from 2? Okay, so 2, 2, 2, 2, 2. I suppose for larger numbers we get 7. Okay, so let's take this to its logical conclusion. Not really the logical conclusion, but another 1,000 steps. And again, we're giving it 40. I don't know, might as well. As long as you're not outputting the lines, why not? Okay, so we still have divergence. What's that? 133. What is that? 133. 11. 11 cubed. That's it. 11 cubed. Okay, that's interesting. So now we've gone another 1,000, and now it's 11 cubed. So the first 1,000 digits produce 7 cubed, and 2, I suppose. And now we've got 11 cubed. That's fascinating. Any more? Last one, guys. Last one. That's I don't know, 5,000 to 10,000 or so, and I'm not going to go up to all those. What do you have? So it's not even going to let me go up 10,000. But I think you get the point. I really think you get the point. There we go. Okay, so nothing after that. But there it was. Just the first 1,000 digits produced 7 cubed. I'm really pleased with all that. Guys, I'll leave it there. I might have another brainwave for next week on the rat sequence, but that was really cool. That was really, really fascinating. Um, yeah, I hope you enjoyed that. Let me know what you thought. Any comments, questions, or anything. If you're studying these sort of things, I don't believe they teach this stuff in primary school, secondary school, maybe at university. I don't recall this in university at all. Then again, I didn't even study the sequence and the series part of the. It was a module, but I didn't study the actual go all the way with it. Anyway, let me know if you're studying this or if you're studying any other John Conway's works or anything in digit dynamics. Um, yeah, hope you're enjoying it. And I'll upload this. What day is it? It's October 13th today. October 13th, 2025, Monday. And I'll see you again next week for another episode. I might have something else on this, I might not. We'll see. Thank you very much, guys, and we'll see you soon.